we need to talk about the fastest way to die in the universe. Not the most painful, not the most dramatic, but the fastest, the most absolute, the most inescapable. We need to talk about gamma-ray bursts and what it would mean if one of them pointed at Earth. Right now, somewhere in the universe, a massive star is collapsing. Its core, composed of iron that can fuse no further, has finally surrendered to gravity. In less than a second, the core compresses from the size of Earth to the size of a city, and the rebound, the shockwave of that collapse, is tearing through the star's outer layers at a significant fraction of light speed. The star explodes. A supernova, bright enough to briefly outshine its entire galaxy. But that's not the dangerous part, that's just the opening act. As the core collapses past the point where even neutron degeneracy pressure can resist, it forms a black hole. And in the microseconds of that formation, in the chaotic swirl of matter and magnetic fields and space-time itself being warped beyond recognition, something else happens. Two jets of energy emerge from the poles of the collapsing core. Not ordinary energy. Not heat or light or even the radiation from a normal supernova. These are beams of gamma rays, the highest energy photons that exist, accelerated to 19^999% of the speed of light, focused into cones narrower than a few degrees, and carrying the energy equivalent of the sun's entire lifetime output compressed into seconds. These are gamma-ray bursts, the most energetic events in the universe since the Big Bang, and if one of them is pointed at you, you don't get a warning, you don't get time to prepare, you don't get to say goodbye, you just end. Let's understand what we're dealing with. Let's map the physics of extinction before we learn whether we need to fear it. Gamma rays are electromagnetic radiation, like visible light or radio waves, but with wavelengths measured in picometers, billions of times shorter than the light your eyes can see. Their photons carry millions of electron volts of energy, enough that each individual photon can break apart molecules, ionize atoms, shatter the chemical bonds that hold biological structures together. A single gamma-ray photon hitting your DNA can cause mutations. A beam of gamma rays, trillions upon trillions of photons per second, doesn't cause mutations. It erases biology. It breaks down the molecules of life into constituent atoms and keeps going, penetrating deep into matter, interacting with nuclei themselves. Gamma-ray bursts release more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. And they focus that energy into beams so narrow, so precisely aimed, that if you're in the beam's path, you receive an intensity of radiation that nothing biological can survive. How narrow are these beams? Typically between 1 and 10 degrees. That sounds wide until you realise how vast the universe is. A 10-degree cone extending across a galaxy is still incredibly focused. It's like a lighthouse beam sweeping across an ocean, narrow compared to the lighthouse's full surroundings. But if you're in the beam, you experience the full intensity of the light. Now imagine the lighthouse is putting out more energy than 1 billion suns, and imagine it's not visible light but gamma rays, and imagine it's pointed directly at you. That's a gamma ray burst, and we've detected thousands of them. They happen roughly once per day somewhere in the observable universe. Most are in distant galaxies, billions of light years away. The energy has had billions of years to spread out, to dilute, to become harmless by the time it reaches us. But one will eventually happen close, in our galaxy, perhaps in our stellar neighbourhood, and if we're unlucky, if the geometry aligns in the worst possible way, one of those jets will point toward Earth. We wouldn't see it coming. Gamma rays travel at the speed of light, which means the first indication that a gamma ray burst is heading toward us would be the burst itself. No warning, no advanced detection, just a sudden flood of the highest energy radiation in the universe, washing over our planet at 300,000 kilometers per second. Let's talk about what happens in the first second. The gamma rays hit Earth's atmosphere. They don't interact with air the way visible light does, gently scattering, creating blue skies and red sunsets. Gamma rays slam into nitrogen and oxygen molecules with enough energy to shatter them completely. Atomic nuclei break apart. The atmosphere ionizes instantly. If you're on the day side of the planet, if the gamma ray burst arrives when you can see the part of the sky it's coming from, you might see a flash. Not a gamma ray flash. Gamma rays are invisible to human eyes. But the secondary radiation, the cascade of lower energy photons produced as the gamma rays tear through the atmosphere, might be visible. A sudden brightening, yes, of the sky, brighter than the sun, lasting seconds. And then the destruction begins. The ionization of the upper atmosphere creates nitrogen oxides on an enormous scale. These compounds, normally present in trace amounts, suddenly fill the stratosphere, and nitrogen oxides are extraordinarily efficient at destroying ozone. Earth's ozone layer, the thin shell of O3 molecules in the stratosphere that absorbs ultraviolet radiation from the sun, begins to disintegrate. Within hours, within days, the ozone layer is gone. Not depleted, not thinned, gone. Destroyed so thoroughly that it would take decades or centuries to recover, if it recovers at all. And without the ozone layer, Earth's surface is exposed to the sun's full ultraviolet output. UVC radiation, the highest energy ultraviolet that's normally blocked completely by ozone, reaches the surface. It's sterilizing radiation. It breaks down DNA. It kills bacteria, algae, the microorganisms at the base of every ecosystem on Earth. Phytoplankton in the oceans begin to die. These microscopic organisms produce more than half of Earth's oxygen and form the foundation of marine food webs. As they die, they stop photosynthesizing. Oxygen production drops. The food web collapses from the bottom up. On land, plants experience severe stress. Crops fail. Forests begin to die back, especially at high altitudes and latitudes where UV exposure is most intense. The productivity of ecosystems plummets. And this is just the atmospheric and ecological response. The gamma rays themselves, the ones that made it through the atmosphere, have been interacting with living tissue. If you were outside when the burst hit, if you were on the hemisphere facing the source, you received a dose of radiation unlike anything a human has experienced in the modern era. Not the slow accumulation of background radiation, not the acute dose from a nuclear accident. A flash of gamma rays intense enough to feel. You might feel warmth, the energy depositing in your tissues, breaking molecular bonds, creating heat as a byproduct. You might feel tingling, the sensation of your nervous system being directly stimulated by high-energy photons. You might feel nothing at all, might not realize anything has happened until hours later when the radiation sickness begins. Your cells are damaged. DNA strands broken in millions of places. Proteins denatured. Membranes disrupted. The damage is catastrophic at the molecular level, and your body's repair mechanisms, evolved to handle normal background radiation, are completely overwhelmed. Within hours, you feel nauseous. Within days, your immune system begins to collapse as white blood cells die faster than they can be replaced. Within weeks, you're experiencing multi-organ failure. Your intestines can't absorb nutrients, your bone marrow can't produce blood cells, your skin is breaking down, there's no treatment. Radiation sickness at these doses is beyond what medicine can address. You can be made comfortable, but you cannot be saved. And you're not alone. Everyone on your hemisphere who was outside received similar doses. Hundreds of millions of people, maybe billions, all dying from acute radiation syndrome simultaneously. But that's just the immediate effect. The long-term consequences are worse. Let's jump forward 6 months. The gamma ray burst lasted 10 seconds. The immediate radiation exposure is long over, but Earth is dying. The ozone layer hasn't recovered. UV radiation is still flooding the surface. Phytoplankton populations have crashed by 90% or more. Oxygen levels in the atmosphere are dropping. Not catastrophically, there's still plenty to breathe, but measurably. More concerning, the food chain has collapsed. Fish populations are crashing as their food source disappears. Seabirds are starving. Coastal ecosystems are dying. And on land, the loss of insect populations. Many insects are extremely sensitive to UV radiation, is causing cascading failures in pollination and decomposition. Agriculture is failing globally. Crops won't grow in the intense UV, or if they do grow, they produce malformed, nutrient-poor yields. Livestock are dying from starvation and UV exposure. The human population, already reeling from billions of radiation deaths, is facing famine. Governments collapse, supply chains break down, cities become uninhabitable as infrastructure fails and food runs out. The survivors retreat to caves, to underground shelters, anywhere they can escape the ultraviolet death that makes the surface hostile to life. Earth has become a different planet, still orbiting the sun, still rotating, still maintaining its atmosphere and oceans. But the biosphere, the thin layer of life that covers the surface, is dying, and the gamma-ray burst, it's long gone. The beam that destroyed Earth has continued past us, travelling through space at light speed, perhaps crossing another star system, perhaps hitting another world, perhaps just spreading into the emptiness between galaxies. The star that produced it doesn't know what it did. It's dead, collapsed into a black hole or neutron star, its explosion fading from view. And we're left with the consequences, with a world rendered nearly uninhabitable by 10 seconds of radiation from a stellar corpse, thousands of light years away. This is the horror of gamma-ray bursts. Not that they're aimed at us. They almost certainly aren't. Not that they're common in our neighbourhood. They're extraordinarily rare. But that if one does happen close enough and pointed at us, there's no defence, no warning, no possibility of survival for most complex life on Earth. We're vulnerable to a threat we can't control, can't predict, and can't survive if it occurs. Let's talk about probability now, because that's the question that matters. How likely is this to happen? Gamma-ray bursts require specific conditions. The collapsing star needs to be massive at least 25 or 30 times the mass of our Sun. It needs to be rotating rapidly. It needs to have the right magnetic field configuration to channel the explosion's energy into jets rather than a spherical blast. These conditions are rare. Most stars aren't massive enough. Most massive stars don't rotate fast enough or have the right magnetic properties. The fraction of stellar deaths that produce gamma-ray bursts is small, perhaps 1 in 100,000 supernovae or fewer, and even when a gamma-ray burst occurs, the jets are narrow. If the beam is 10 degrees wide, then only about 0.5% of the sky around the burst is in the danger zone. 99.5% of surrounding space is safe, untouched by the jets. So the odds of any particular gamma-ray burst affecting Earth are incredibly low. We'd need a massive star to die within our galaxy, rare. We'd need it to produce a gamma-ray burst, very rare. We'd need one of the jets to point at Earth, extremely rare. Multiply these probabilities together and you get numbers that are comforting. The chance of a gamma-ray burst hitting Earth in any given year is perhaps 1 in a million, or 1 in 10 million, or even less depending on whose calculations you trust. Over human lifetimes, the risk is negligible. Over the span of recorded history, negligible. Over the entire history of human civilization, negligible. But over geological time, over hundreds of millions of years, the probabilities start to add up. Earth has existed for 4.5 billion years. Life has existed for nearly 4 billion of those years. Complex life for 600 million years. In that time, how many gamma-ray bursts might have hit Earth? We don't know. We can't know. Gamma-ray bursts don't leave obvious geological signatures. They don't create impact craters. They don't deposit unusual elements in sedimentary layers. The ozone destruction and UV radiation would cause mass extinctions. But mass extinctions can have many causes, and we can't always distinguish between them in the fossil record. But statistically, over 600 million years, Earth has probably been hit by at least one gamma-ray burst, maybe several. The Ordovician mass extinction 450 million years ago has features consistent with ozone layer destruction and UV damage. It's not proof. Other mechanisms could explain the same evidence, but it's suggestive. If gamma-ray bursts have caused mass extinctions in the past, they could cause them again in the future, not tomorrow. Not in our lifetimes. But eventually, on timescales measured in tens or hundreds of millions of years, another massive star in our galactic neighbourhood will die, will produce a gamma ray burst, and will, through sheer chance, point one of its jets toward us. And when that happens, most life on Earth will end. Not all life. Extremophiles in deep caves and deep ocean vents would survive, but most surface life, most complex ecosystems, most of the biosphere, and if humanity still exists as a single planet species, if we haven't spread to other worlds by then, we'll end too. Let's make this more visceral. Let's talk about what it would actually feel like to experience a gamma ray burst, not as abstract physics, but as human sensation. You're outside on a clear day. You're going about your life, working, walking, enjoying the sun. The sky is blue. The world is normal. And then, in an instant, everything changes. The sky brightens, not gradually, not like a sunrise, but instantly. One moment it's normal daylight. The next moment it's as if a second sun has appeared, overwhelming the first. You instinctively look up, trying to find the source, and the brightness hurts even though you're not looking directly at it. Your skin feels warm, warmer than it should from sunlight. There's a tingling sensation, subtle but wrong, like static electricity but deeper, like your nerves are firing randomly. You don't know what's happening. No one does. There's no context for this experience. It's not an eclipse, not an aurora, not anything in human experience. The brightness lasts seconds, 10 seconds, 20. It fades as quickly as it came. The sky returns to normal blue. The warmth stops. The tingling fades. You look around. Other people are confused, are checking their phones or asking each other what that was. Some people felt nothing. They were indoors or on the wrong hemisphere. But those who were outside, who had a clear sky above them, all experienced something similar. You go home, you check the news. There's nothing, no explanation. Scientists are baffled. Astronomers are checking their instruments, looking for anything unusual in the sky. But gamma rays are invisible to optical telescopes, and the specialized satellites that detect gamma rays take time to analyze their data. Hours pass. You start to feel unwell, nausea, fatigue. You think maybe you have the flu, maybe you ate something bad. You lie down to rest. The next day you're worse. The nausea is intense. You're vomiting. Your skin feels tender, almost sunburned but not quite. And now the news is reporting something strange. Hospitals are overwhelmed with people experiencing similar symptoms. Everyone who was outside yesterday, everyone who saw the bright sky, is sick. Scientists have figured it out. The satellites detected it. A gamma ray burst, one of the closest ever recorded, close enough that Earth was within the beam's path. You've been irradiated. Everyone on your hemisphere has been irradiated. The dose was massive, far beyond what medical science can treat. And there's more. The burst destroyed the ozone layer. UV radiation is now flooding the surface. Going outside during the day is dangerous. Crops are failing. The ocean is dying. The biosphere is collapsing. You have maybe weeks to live, maybe months if you're lucky. But the world you're living in is dying faster than you are, and there's nothing anyone can do about it. This is the human experience of a gamma ray burst, not the abstract physics of ionization and ozone depletion, but the lived reality of dying from radiation sickness while watching civilization collapse around you. It's a slow apocalypse following a fast catastrophe. The burst is quick, almost anticlimactic. The dying takes time, takes effort, takes watching the world unravel day by day, and it's completely, utterly beyond human control. We didn't cause it, we can't stop it. We can only experience it and endure it for as long as our damaged bodies allow. Let's talk about detection now, because you might be wondering, can we see these coming? Can we get any warning at all? The answer is no, not for the gamma rays themselves. Gamma rays travel at the speed of light. If a gamma ray burst is heading toward Earth, The first gamma-ray photons to arrive are travelling at exactly the same speed as any warning signal we might detect. There's no way to get advance notice because there's no way for information to travel faster than light. We might detect precursor signals, theoretically. Some gamma-ray burst models predict that gravitational waves or neutrinos might be emitted slightly before the gamma rays themselves, travelling at or near light speed but potentially detectable earlier if we have the right instruments looking in the right direction. But this is a matter of seconds at most. Even if we detected gravitational waves from a stellar collapse and correctly interpreted them as precursors to a gamma-ray burst pointing toward Earth, we'd have maybe 10 seconds of warning. What could we possibly do in 10 seconds? Tell people to go inside. The gamma rays will penetrate buildings, not as effectively as they penetrate atmosphere, but enough to deliver dangerous doses to anyone not in a deep bunker. Evacuate. To where? The burst affects an entire hemisphere. There's nowhere to run in 10 seconds. The truth is, advance warning of seconds would be essentially useless. It might allow scientists to make final observations, might give people time to send last messages to loved ones if the communication networks held up. But it wouldn't save anyone. What about longer-term warning? Can we identify stars that might produce gamma-ray bursts and monitor them? Yes, to an extent. We know which types of stars are candidates. Wolf-Rayet stars, massive stars that have shed their outer layers and are nearing the end of their lives. We can catalogue these stars, can watch them for signs of instability. But we can't predict when they'll collapse. Could be tomorrow. Could be 1,000,000 years from now. We can't know. And even if we could predict the timing, we can't predict the jet direction. The jets are determined by the star's rotation axis and magnetic field configuration at the moment of collapse. We can't measure these properties precisely enough to predict where the jets will point, so we can identify potential sources, can say this star might produce a gamma-ray burst someday, but we can't say when or whether it would affect Earth. We're essentially flying blind, living under a sky that might at any moment flash with lethal radiation and having no reliable way to predict or prevent it. The only comfort is statistics. The universe is vast. Dangerous stars are far away. The odds are in our favour, at least on human timescales. But odds aren't certainties, and over cosmic time, even improbable events occur. Let's talk about the survivors, because even in the worst-case scenario, some humans might survive a gamma-ray burst. Not many, not most, but some. If you're on the night side of the planet when the burst hits, you're shielded by Earth itself. The gamma rays can't penetrate through 12,000 kilometers of rock and metal. The far side of the planet experiences no direct radiation exposure. But you're not safe. The ozone destruction is global. Atmospheric circulation will spread the nitrogen oxides around the planet within weeks. The UV radiation will affect you too, just delayed slightly. And the societal collapse affects everyone. Food production fails globally. Supply chains break down. Even if you personally survive the radiation, you're living in a world where most of the population has died or is dying, where the infrastructure that supports modern life is crumbling. Who survives long term? Those who can reach deep shelters and stay there. Submarine crews, perhaps, or people in deep caves with stored food and water. The very rich who've built bunkers designed to survive nuclear war, those would work for gamma-ray bursts too, assuming the life support systems hold up. But these survivors would emerge into a devastated world. The surface would be recovering slowly, the ozone layer gradually rebuilding over decades. Plant life would be starting to return, but the ecosystems would be shattered, reorganized into new configurations. Humanity might persist, might rebuild, but we'd be set back centuries or millennia. The technological civilization would be gone, and the surviving populations would be small, isolated, struggling to survive in a world that's hostile to complex life. This is the best-case scenario for a close gamma-ray burst. Partial survival, partial extinction. A bottleneck that humanity might squeeze through, but only barely, and only at enormous cost. The worst case scenario: the burst is close enough and powerful enough that even the night side isn't safe, that enough gamma rays scatter through the atmosphere and wrap around the planet to deliver lethal doses globally. Or the secondary effects, the ozone destruction, the UV radiation, the ecosystem collapse, are so severe that no surface survival is possible. In that case, only the deeper shelters survive. Only the people who can live underground for years or decades, who have the resources and infrastructure to wait out the surface sterilization. And maybe they make it. Maybe some small population of humans persists deep in the earth and eventually returns to the surface when it's safe. Or maybe they don't. Maybe the shelters fail. Maybe the populations are too small to maintain genetic diversity. Maybe the psychological strain of living underground for decades, knowing the surface world is dead, is too much. In that case, humanity ends. Not with a bang, but with small groups of survivors slowly dying in bunkers, the last humans to ever exist closing their eyes for the final time while the surface world, sterile and empty, slowly recovers without us. That's the true horror of gamma-ray bursts. Not just that they can kill us, but that they can kill us so thoroughly, so completely, that nothing of human civilization survives. No ruins for future species to discover. No fossils to show we existed. Just a gap in the geological record. A period where complex life declined sharply and then, slowly, returned in different forms. We would be gone as if we never existed, and the universe, indifferent as always, would continue without pause or acknowledgement. Let's shift perspective now. Let's talk about what gamma-ray bursts tell us about the universe's fundamental nature, about the cosmos as a place where violence operates on scales we can barely comprehend. Gamma-ray bursts are not anomalies. They're not glitches in an otherwise peaceful universe. They're a natural consequence of stellar evolution, as inevitable as sunrise, as common as rain. Somewhere in the observable universe, one is happening right now as you listen to these words, and another will happen in the next few hours, and another after that. The universe is constantly producing these beams of annihilation, these jets of energy that could sterilize worlds, and it does so without awareness, without intention, as casually as a star produces light. What does that tell us about the cosmos we inhabit? It tells us that the universe operates at energy scales that dwarf anything biological. A gamma-ray burst releases in seconds what our sun will produce in its entire lifetime. That's not an attack on us. It's not aimed at life. It's just physics operating at the high end of its range. We exist at the low energy end of the cosmic spectrum. We're warm-blooded creatures on a temperate world, dealing with energies measured in calories and kilowatts. We build power plants that produce gigawatts. We detonate nuclear weapons that release megatons. Gamma-ray bursts operate in a different realm entirely. They're measured in solar luminosities, in masses converted directly to energy via Einstein's equation, in jets that could power our entire civilization for billions of years if we could somehow capture even a fraction of their output. The universe doesn't care about the energy scales that life requires. It produces events across the full range that physics allows, from the gentle warmth of sunlight to the apocalyptic fury of colliding neutron stars and collapsing massive stars. We happen to exist in a relatively quiet era, in a relatively quiet region of space. Our sun is stable. Our neighbourhood is free of recently exploded supernovae. We're far from the galactic centre where stellar density is high and violent events are more common. We're in the suburbs of the galaxy, in a cosmic calm, and we've mistaken that calm for the universe's default state. It isn't. The default state of the universe is chaos and violence. Stars explode, black holes collide, galaxies merge and tear each other apart. Gamma-ray bursts scour regions of space clean of complex chemistry. Life exists in the gaps between these events, in the quiet moments, on worlds lucky enough to be far from the violence. We're not the norm. We're the exception. We're the brief, peaceful moment in a cosmos that's fundamentally turbulent. And that turbulence doesn't pause for our convenience. It doesn't check whether life has evolved on nearby worlds before a massive star collapses. It just happens, following the laws of physics, indifferent to consequences. This is a hard truth. We want the universe to be hospitable, or at least neutral. We want to believe that if we're careful, if we're smart, if we understand the risks, we can make ourselves safe. But gamma-ray bursts remind us that safety is an illusion. We're safe only because we've been lucky so far, because no nearby star has collapsed in the wrong orientation in the time it took for human civilization to develop. That luck could end tomorrow, or it could last for billions of years. We don't control it. We can't influence it. We can only exist in the present moment and hope the present extends into future moments similar enough that life can continue. Let's talk about other worlds now. Other planets that might have been hit by gamma-ray bursts. Other civilizations that might have been destroyed by them. If life is common in the universe, if planets with liquid water and stable stars frequently develop biology, then gamma-ray bursts are one of the major filters that prevent that life from becoming technological, from spreading beyond its home world, from becoming visible to us. The Great Filter is the concept that somewhere between non-life and galaxy-spanning civilizations, there's a step that's extraordinarily difficult to pass. Most potential civilizations fail at this step, which is why we don't see evidence of other technological species despite the universe being old and vast. Maybe the filter is a biogenesis, the origin of life itself. Maybe it's the development of complex cells. Maybe it's intelligence. Maybe it's the tendency of intelligent species to destroy themselves with their own technology. Or maybe one of the filters is cosmic. Maybe many civilizations develop intelligence, build technology, reach toward the stars, and then a gamma-ray burst happens in their stellar neighborhood and they're sterilized before they can spread. Imagine an alien world, similar to Earth, orbiting a sun-like star with oceans, and continents and an atmosphere rich in oxygen. Life has evolved there for billions of years. Intelligence has emerged. They've built cities, developed science, created art and philosophy and mathematics. They're wondering if they're alone in the universe, just like we are. They're looking at the stars and asking if anyone else is out there. And then, without warning, a massive star 3,000 light-years away collapses. The gamma-ray burst jets sweep across their region of space. Their planet is in the beam. 10 seconds of radiation, their ozone layer destroyed, their biosphere collapsing, their civilization ending not because they did anything wrong, not because they failed some test, but because they were unlucky, because the geometry of stellar death happened to align with their position in space. If this happens frequently, if gamma-ray bursts are efficient at sterilizing planets around nearby stars, then the galaxy might be full of dead worlds. Planets where life arose, flourished, achieved complexity and maybe even intelligence, and then was erased by a beam of energy from a dying star. We wouldn't see evidence of these civilizations. They didn't last long enough to build megastructures or send out radio signals that we could detect. They just ended, and their worlds slowly recovered, life starting over from extremophils and simple organisms, re-evolving complexity if conditions allowed. The galaxy might be full of these resets. Worlds hit by gamma-ray bursts every few 100 million years, their biospheres periodically sterilized, life constantly starting over, never getting the uninterrupted billions of years needed to develop technology and spread to other stars. Earth might be unusual not because life arose here, that might be common, but because we've had 4 billion years of uninterrupted development. We haven't been hit by a close gamma-ray burst in that time. We've been lucky, and our luck might be running out, or it might continue for billions more years. There's no way to know. But if gamma-ray bursts are indeed a major filter, if they're one of the reasons we don't see evidence of other civilizations, then our urgency to become a multi-star species increases dramatically. because staying on one world in one star system means accepting that a single gamma-ray burst could end us. But spreading to multiple star systems, distributing humanity across dozens or hundreds of worlds, means that a gamma-ray burst can only destroy part of us, not all of us. It's the same logic as the rogue black holes. Resilience through distribution. Don't try to prevent the threat, you can't. Make yourself robust enough to survive it. Let's talk about the physics in more detail now, because understanding how gamma-ray bursts work helps us understand both why they're so dangerous and why they're so unlikely to affect us. The leading model for long-duration gamma-ray bursts, the ones lasting more than 2 seconds, is the collapsar model. A massive star, having burned through all its nuclear fuel, has a core of iron. Iron can't fuse into heavier elements and release energy. Fusing iron actually consumes energy. So the core can't support itself against gravity anymore. The core collapses. In less than a second, it goes from a sphere 3,000 kilometers across to a sphere 30 kilometers across. That's a 100-fold reduction in radius, which means the density increases by a factor of 1,000,000. The collapse releases gravitational potential energy, a lot of it. Most of this energy goes into neutrinos, ghostly particles that barely interact with matter and carry the energy away into space. But some of the energy goes into heating the material surrounding the core. If the star is rotating rapidly, the infalling material doesn't fall directly onto the core. It forms an accretion disk, a swirling disk of superheated matter spiraling inward. The disk generates powerful magnetic fields, and these fields channel energy along the rotation axis. 2 jets form, emerging from the poles of the disk, driven by magnetic pressure and radiation pressure. These jets punch through the collapsing star's outer layers, and when they emerge into space, they're moving at 99.9999% of the speed of light, carrying gamma rays and accelerated particles. The jets are narrow because they're focused by magnetic fields and by the geometry of the accretion disk. They're powerful because they're tapping into the gravitational potential energy of a stellar core collapsing into a black hole, one of the most energy-dense processes in the universe. And they last for seconds to minutes because that's how long it takes for the accretion disk to drain, for the material to either fall into the black hole or be blown away by the jets themselves. This is a collapsar, a collapsing massive star that produces a gamma-ray burst. They happen when stars at least 25-30 solar masses die, and they happen preferentially in galaxies with low metallicity, where stars retain more of their mass and rotation through their lifetimes. Our Milky Way has relatively high metallicity. Stars here tend to lose mass through stellar winds, which slows their rotation and makes collapsar gamma-ray bursts less likely. That's good for us. It means the rate of gamma-ray bursts in our galaxy is lower than in some other galaxies, but it's not zero. Even in the Milky Way, massive stars occasionally die with the right properties to produce gamma-ray bursts, and when they do, those jets sweep through nearby regions of space, and if any worlds happen to be in the way, those worlds pay the price. There's another type of gamma-ray burst, short-duration bursts, lasting less than 2 seconds. These are produced by different mechanisms, typically the merger of 2 neutron stars or a neutron star and a black hole. When 2 neutron stars spiral into each other, driven by gravitational wave emission over millions of years, the final moments of the merger release enormous energy. Some of that energy goes into gravitational waves. We've detected these signals. Some goes into neutrinos, and some, if conditions are right, goes into gamma-ray jets. Short bursts are less powerful than long bursts on average, but they're still dangerous, and they're harder to predict because we can't see neutron star binaries as easily as we can see massive stars approaching death. A neutron star binary could be spiraling toward merger in our galactic neighborhood right now, and we might not know it until the merger happens and the gamma-ray burst emerges. So we face threats from 2 sources: massive stars that we can at least identify and catalogue, and compact object mergers that we mostly can't see coming. Both are rare, both are unlikely to affect Earth on human timescales, but both are real, both happen regularly in the universe, and both could, in principle, end most life on our planet. Let's think about distance now, because that's the key variable. How close does a gamma-ray burst need to be to threaten Earth? For a typical long-duration gamma-ray burst, one lasting 10 seconds and releasing 1051 ergs of energy, about 1044 joules, the dangerous distance depends on the opening angle of the jets and the total energy. If we're in the jet's direct path, a burst within 10,000 light-years could deliver enough gamma radiation to significantly damage the ozone layer. Within 6,000 light-years, the damage would be severe, mass extinction level. Within 3,000 light-years, it would be catastrophic, nearly complete sterilization of surface life. Those distances might sound comforting. The Milky Way is 100,000 light-years across. There's a lot of space to hide in, but there are billions of stars in the galaxy, and massive stars, while rare, aren't absent. Within 10,000 light-years of Earth, there are millions of stars. Most are small, safe, incapable of producing gamma-ray bursts, but some are massive. Some are Wolf-Rayet stars, blue supergiants, hypergiants, stars massive enough and unstable enough to potentially produce collapsar gamma-ray bursts. We can catalogue these stars, we can watch them, but we can't predict when they'll die, or where their jets will point. The nearest known candidate is probably WR104, a Wolf-Rayet star about 8,000 light-years away. It's rotating rapidly, it's in a binary system, which might affect its evolution and jet formation, and its rotation axis might be oriented toward Earth, though the measurements are uncertain. If WR104 were to collapse tomorrow and produce a gamma-ray burst with one of its jets pointing at us, we'd be in serious danger. Not complete sterilization, 8,000 light-years is far enough that the flux would be diluted, but significant ozone depletion, ecosystem damage, potential mass extinction. Should we be afraid of WR104? Not particularly. The uncertainties are enormous. We don't know when it will collapse. Could be tomorrow, could be 100,000 years from now. We don't know if it will produce a gamma-ray burst. It might just explode as a normal supernova. We don't know the jet orientation. It might be pointed away from us. The risk from WR104 specifically is small, but WR104 is just one star. There are others, and over millions of years the cumulative risk from all massive stars in our galactic neighbourhood adds up. Let's talk about what we could do if we detected a nearby star about to collapse and suspected it might produce a gamma-ray burst pointing toward Earth. First, we can't stop the star from collapsing. We can't prevent the gamma-ray burst. The energies involved are so far beyond human capability that even discussing intervention is absurd. We might as well try to stop the Earth's rotation by running in the opposite direction. Second, we can't shield Earth from gamma rays. There's no material we could put in space that would absorb a gamma-ray burst's energy. We'd need something with the mass of a planet, and we'd need to position it precisely between Earth and the burst source, which is impossible on any reasonable timescale. Third, we can't evacuate. Where would we go? Mars? Mars would be hit by the same burst. The Moon? Same problem. Other star systems? We don't have faster-than-light travel. By the time we detected the imminent collapse, we'd have at most days or weeks of warning, and we can't evacuate billions of people in that time. So what could we do? We could prepare. We could build deep shelters designed to withstand gamma-ray bursts, stocked with food and water and air recycling systems, designed to keep populations alive underground for years while the surface biosphere recovers. We could preserve genetic diversity, seed banks, DNA repositories, frozen embryos of endangered species, stored in radiation-hardened facilities deep underground. We could develop technologies for atmospheric engineering, for rapidly rebuilding the ozone layer, for protecting crops and ecosystems from UV radiation. None of these are solutions, they're mitigation strategies. They reduce the harm but don't eliminate it. Millions would still die, ecosystems would still collapse, civilization would still be devastated, but some would survive. And given enough preparation, given enough resources dedicated to resilience, humanity might persist through even a relatively close gamma-ray burst. The question is, are we willing to invest in preparation for a threat that might not materialize for millions of years? Are we capable of planning on timescales that exceed individual lifetimes, or even the lifespans of nations? History suggests we're not good at this. We struggle to address climate change, a threat with a timescale of decades to centuries. How could we mobilize resources for a threat with a timescale of millions of years? Maybe we can't. Maybe we just accept the risk and hope we're lucky. Hope that by the time a nearby gamma-ray burst occurs, if it ever does, we've naturally evolved into a multi-star species for other reasons, and the burst can only affect one of our worlds rather than all of them. Hope isn't a strategy, but when the threat is this powerful and this rare, hope might be all we have. Let's talk about the human psychology of living with this knowledge, because that's ultimately what we have to do. We have to know that gamma-ray bursts exist, that they could kill us, and still get up in the morning and live our lives. How do you do that? How do you reconcile the cosmic vulnerability with the need to plan, to build, to create long-term value? One approach is compartmentalization. You acknowledge the threat intellectually, but don't let it affect your emotional state or your daily decisions. Yes, a gamma-ray burst could sterilize Earth tomorrow. Yes, I could also die in a car accident or from a sudden aneurysm, or from any of 1,000 causes I can't predict or control. Life is uncertain. I live anyway. This is healthy to an extent. You can't function if you're constantly aware of every possible threat. The human brain is designed to focus on immediate, actionable concerns and to background the distant or uncontrollable ones. But there's a risk of going too far, of denying the threat entirely, of pretending we're safer than we are. If we forget that the universe is dangerous, if we assume our current safety is permanent, we might fail to take reasonable precautions, might fail to become an interstellar species when we have the chance. Another approach is acceptance, not fatalistic resignation, but clear-eyed recognition that we live in a dangerous universe and that's okay. We're not entitled to safety. We're not promised a future. We're here now, experiencing existence, and that's remarkable regardless of how long it lasts. This approach leads to presence, to appreciating the moment, to finding meaning in the immediate rather than deferring it to some imagined permanent future. A third approach is proactive engagement. Channel the awareness of cosmic threats into motivation for space exploration, for scientific research, for building resilient systems and backup plans. Use the fear as fuel for progress rather than paralysis. All three approaches are valid. You might use different ones at different times. The key is finding a relationship with the knowledge that allows you to continue functioning, continue creating, continue engaging with life despite the uncertainty. Because the alternative, giving up, despairing, concluding that nothing matters because it might all end suddenly, is a kind of death itself. Not physical death, but the death of meaning, of purpose, of engagement with the world. Gamma-ray bursts can kill your body. Don't let the knowledge of them kill your spirit. Let's shift into deeper contemplation now. Let's move from the mechanics of destruction to the philosophy of existing in a universe where such destruction is possible, where beams of annihilation sweep through space as a natural consequence of stellar death. There's something profoundly humbling about gamma-ray bursts. They remind us that the universe doesn't care about complexity, doesn't value consciousness, doesn't preserve the intricate structures that took billions of years to evolve. A gamma-ray burst doesn't distinguish between a sterile rock and a planet teeming with life. It doesn't spare worlds where civilizations have arisen, where beings have asked questions about their origins and their fate. It just propagates through space according to the laws of physics, depositing energy wherever it encounters matter, indifferent to consequences. This indifference is hard to accept. We want the universe to be meaningful, to reflect our values, to operate according to principles that include preservation of life and consciousness. We want to believe that because we value ourselves, The cosmos values us too, but it doesn't. The cosmos has no values. It has no preferences. It simply is, operating according to physical law, producing everything that physics allows, including life when conditions permit, and including the destruction of that life when stellar evolution happens to create beams of gamma rays that intersect inhabited worlds. We're not special in the cosmic scheme. We're fortunate. We exist in a time and place where the conditions allow for our existence. But that fortune is temporary and contingent, dependent on variables we don't control. A gamma ray burst doesn't need to happen for this to be true. Even without external cosmic threats, we're temporary. The sun will eventually die. Earth will eventually become uninhabitable. Given enough time, entropy ensures that all complex structures dissolve. Gamma ray bursts just make the temporariness more immediate, more visceral, more undeniable. They could shorten our timeline from billions of years to tomorrow, and we'd have no say in the matter. How do we find meaning in such radical contingency? The traditional answer is to find meaning in permanence, in creating things that last, in being remembered. But if a gamma ray burst can erase not just us, but the conditions that allow for memory itself, then permanence-based meaning fails. We need a different foundation, meaning that doesn't depend on duration, on preservation, on echoes into the future. Meaning in the immediate, in the quality of experience rather than its quantity, in the depth of awareness rather than its extension through time. You're alive now, you're conscious now, you're experiencing the universe knowing itself through your particular perspective. And that's complete in itself. It doesn't need to last forever to be meaningful. A sunset is beautiful even though it fades. Music is moving even though it ends. Consciousness is valuable even though it's temporary. Gamma ray bursts threaten the continuation of consciousness, but they can't erase the fact that consciousness has occurred. You've existed. You've been aware. And nothing, not even the most powerful beams in the universe, can undo the fact that existence happened. The past is immutable. What has been, and what you are experiencing right now, in this present moment, is contributing to that immutable past with every passing second. A gamma ray burst could prevent your future. It can't erase your present or your past. Find meaning there, in the eternal now that's constantly becoming eternal past, in the accumulation of moments of awareness that constitute your existence, each one complete in itself, each one adding to the total sum of consciousness that has occurred in the universe. This isn't easy. We're conditioned to think in terms of future, of progress, of building towards something that will outlast us. But maybe that conditioning is a mistake. Maybe the future is a distraction from the only time that's real, now. Gamma ray bursts are teachers in this sense. They force us to confront impermanence. They strip away the illusion of guaranteed futures. They leave us with the present stark and immediate and all we truly have. Let's talk about other forms of cosmic radiation now, because gamma ray bursts aren't the only threat of this type. They're perhaps the most dramatic, but there are others worth understanding. Supernovae themselves, even without gamma ray burst jets, produce dangerous radiation. A supernova within 30 light years could deliver enough X-rays and cosmic rays to damage Earth's ozone layer and affect the biosphere. Not as catastrophically as a gamma ray burst, but enough to cause problems. The good news is that there are no stars within 30 light years of Earth that are massive enough to go supernova. Our nearest stellar neighbours are small, stable stars that will die quietly as white dwarfs billions of years from now. The bad news is that stars move. Over millions of years, stellar orbits around the galaxy shift. A star that's 100 light years away now could pass within 30 light years eventually. And if that star happens to be a supergiant on the verge of death, we could find ourselves in danger without having seen it coming. Then there are magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. When magnetars experience starquakes, sudden rearrangements of their crusts, They can release bursts of X-rays and gamma rays. These magnetar flares aren't as powerful as gamma ray bursts from stellar collapse, but they're still dangerous if they occur close enough. And magnetars are harder to predict than massive stars. We can't see them until they flare, and by then it's too late to do anything but observe and hope we're far enough away. The most powerful magnetar flare ever detected was in 2004, from a magnetar 50,000 light-years away. Despite the enormous distance, the radiation that reached Earth was strong enough to measurably affect our upper atmosphere and temporarily disrupt satellite communications. If that flare had occurred from a magnetar just 1,000 light-years away, the effects on Earth could have been significant. Not extinction level, but enough to damage satellites, disrupt technology, maybe even deliver dangerous radiation doses to astronauts in space. We don't know how many magnetars exist in the galaxy. They're born from the most massive stars, which means they're rare, but the galaxy has produced billions of stars over its history. There could be thousands of magnetars out there, most of them quiet, some of them flaring occasionally, and we don't have a good catalogue. We know about the ones that have flared while we've been watching, but there are surely many we haven't detected yet. So we face threats from multiple types of stellar objects, all capable of producing dangerous radiation, all rare but not absent, all fundamentally unpredictable. The universe is full of loaded guns, and we're living in the shooting gallery hoping none of them happen to be pointed our way when they go off. Let's think about the possibility that Earth has been hit by gamma-ray bursts in the past, because the more we learn about Earth's history, the more we find evidence of cosmic influences on evolution and extinction. The Ordovician mass extinction, 450 million years ago, killed about 85% of marine species. It occurred in two pulses, separated by hundreds of thousands of years, and it's associated with evidence of climate cooling and changes in ocean chemistry. One hypothesis is that a gamma-ray burst caused the first pulse. The burst would have destroyed the ozone layer, allowed intense UV radiation to reach the surface, killed photosynthetic organisms in the upper ocean, and triggered a cascade of ecosystem collapse. The cooling would have resulted from the destruction of atmospheric chemistry. Less ozone means less absorption of solar radiation in the upper atmosphere, which affects global temperature distribution. The second pulse might have been the recovery, or the failure to recover. Ecosystems trying to rebuild but unable to stabilize. Species going extinct not from the initial catastrophe, but from the ongoing instability it created. This is speculative. We can't prove a gamma-ray burst caused the Ordovician extinction, but the pattern fits, and we can't rule it out. If it did happen, if Earth was hit by a gamma-ray burst 450 million years ago, then we know two important things. First, it didn't sterilize the planet. Life survived. The extinction was severe but not total. Complex life recovered, evolved, eventually produced us. Second, it can happen here. Earth is not in some protected zone. We're not exempt from cosmic violence. We're just lucky that the violence has been manageable so far, that the hits we've taken weren't quite strong enough to end complex life entirely. Are we due for another hit? That's not how probability works. Past events don't make future events more or less likely unless they're causally connected. But the existence of past impacts tells us that the threat is real, not just theoretical. Gamma-ray bursts have affected Earth before, they could affect Earth again. The question is not if but when, and whether we'll be prepared when it happens. Let's talk about preparation in more detail, about what a civilization serious about surviving gamma-ray bursts would need to do. First, detection and early warning systems. We need better surveys of massive stars in our galactic neighbourhood. We need to identify every Wolf-Rayet star, every blue supergiant, every hypergiant within 10,000 light-years, and monitor them for signs of instability. We need gravitational wave detectors sensitive enough to pick up the signals from stellar core collapse before the gamma rays arrive. That's a tall order. We might only get seconds of warning, but seconds are better than nothing. We need satellite networks that can detect gamma-ray bursts the instant they occur and triangulate their sources, giving us immediate information about direction and intensity. Second, resilient infrastructure. We need food production systems that can operate underground or in heavily shielded facilities. We need to diversify our agriculture, spread it across multiple continents, develop backup systems that can function even if the surface biosphere collapses. We need genetic repositories in deep storage, preserved against radiation, containing the DNA of as many species as possible. If surface ecosystems collapse, we need the ability to reconstruct them when conditions improve. We need technology that doesn't depend on satellites, since those would be disabled by a gamma-ray burst. Ground-based communication networks, navigation systems that work without GPS, infrastructure that can function during and after a major cosmic event. Third, off-world colonies. This is the long-term solution. If we spread to Mars, to the moons of Jupiter and Saturn, to space, habitats throughout the solar system, then a gamma-ray burst can only affect part of humanity. The beam is narrow. If Earth is in the path, Mars might not be. If Mars is affected, the moons of Jupiter might not be. By distributing ourselves across multiple worlds, we ensure that no single cosmic event can end us. And eventually, if we become truly interstellar, if we establish colonies around other stars, then even a gamma-ray burst in our immediate stellar neighbourhood can only affect our local systems, not the entire species. This is the ultimate resilience, being so distributed, so diverse, so spread out across the cosmos that you can lose entire star systems and still persist. We're nowhere near this yet. We barely have a foothold on Mars. We're decades or centuries away from self-sustaining colonies elsewhere in the solar system. Interstellar colonization is something our descendants might achieve if we survive long enough. But it's the direction we need to move in, not just because of gamma-ray bursts, but because of all cosmic threats. Asteroids, supernova, rogue black holes, the eventual death of our sun, all of them argue for the same solution. Spread out, diversify, become robust through distribution. Staying on one world is a long-term extinction risk. Becoming a multi-world species is the only strategy that offers genuine long-term survival. Let's think about consciousness more deeply now, about what it means to be aware in a universe where gamma-ray bursts sweep through space, where awareness itself can be extinguished by cosmic events. Consciousness is fragile. It depends on precise chemical reactions, on neurons firing in specific patterns, on conditions that are extraordinarily rare in the universe. Most of the cosmos is too hot or too cold, too dense or too diffuse, too radioactive or too empty to support the kind of complexity consciousness requires. Earth provides those conditions, for now, but Earth's hospitality is temporary and contingent. A gamma-ray burst could end it. So could many other things. And yet, despite this fragility, consciousness exists. You exist. You're aware right now, thinking about gamma-ray bursts, contemplating your own vulnerability, experiencing what it's like to be a conscious being in a dangerous universe. That's extraordinary. Not in the sense of special or protected, but in the sense of remarkable, unexpected, worth noting. The universe is mostly unconscious. Stars burn without awareness. Galaxies collide without knowing. Black holes consume without experiencing. Consciousness is the rare exception, the tiny fraction of the cosmos that knows itself, and you're part of that fraction. You're one of the locations where the universe has become self-aware, where matter has organized itself into patterns that can think, feel, wonder, fear. Gamma-ray bursts threaten that awareness. They threaten to return the matter that constitutes you to unconscious forms, to break down the patterns that create your thoughts and experiences. But they can't erase the fact that awareness happened. They can't undo the moments you've experienced, the thoughts you've had, the ways you've participated in the universe's self-knowledge. Your existence contributes to the total sum of consciousness that has occurred in the cosmos, and that sum is real, is valuable. regardless of whether it continues into the future. This is a strange kind of immortality. Not personal immortality. You will die, and your specific pattern of awareness will end. But participation in something larger, the phenomenon of consciousness itself, the universe's ongoing project of knowing itself through temporary configurations of matter like you're mortal. Consciousness as a phenomenon might be mortal too, if gamma-ray bursts and other cosmic threats eventually sterilize all habitable worlds. But while it exists, while you exist, you're part of something genuinely remarkable. Find meaning in that. Participation. In being a temporary node in the network of awareness, experiencing your particular corner of reality, contributing your particular perspective to the cosmos's self-knowledge. Gamma-ray bursts can end your participation. They can't erase the fact that you participated. Let's talk about beauty now, because even in contemplating cosmic destruction, there's something beautiful about the physics, about the universe revealing its capabilities at the extremes. A gamma-ray burst is terrible. It's lethal, catastrophic, capable of sterilizing worlds. But it's also extraordinary. It's stellar death on the grandest scale, matter and energy and space-time pushed to their limits, producing phenomena so extreme that they challenge our understanding of physics. The jets move at 99.99999% of light speed. That's not just fast, that's approaching the cosmic speed limit, the velocity at which relativistic effects become dominant, where time dilates and space contracts and the normal rules of motion break down. The energy density in those jets is enormous. We're talking about conditions similar to the early universe, moments after the Big Bang, compressed into narrow beams and sustained for seconds to minutes. The magnetic fields involved are the strongest we know of, stronger than anything we can create in laboratories, strong enough to affect the structure of atoms themselves. This is physics at the edge of what's possible, and we get to observe it, to study it, to understand it through mathematics and observation and theory. There's beauty in that understanding, even when what we're understanding is dangerous. Beauty in the elegance of the equations that describe jet formation. Beauty in the way relativity and quantum mechanics and thermodynamics all come together to produce these spectacular events. You can hold both truths simultaneously. Gamma-ray bursts are dangerous and beautiful, terrible and awe-inspiring, threatening and magnificent. This is what it means to have a mature relationship with the cosmos. Not denying the danger, not pretending you're safe, but also not reducing the universe to pure threat, not seeing it only as hostile. The universe is indifferent. It produces beauty and danger with equal ease, following physical law without regard for whether the outcomes support life or destroy it. And you, conscious being that you are, can appreciate both aspects, can fear the gamma-ray bursts while also marveling at them, can work to protect yourself while also studying them with fascination. This is the gift of consciousness, the ability to hold contradictions, to experience fear and wonder together, to be appropriately cautious and appropriately curious at the same time. Let's drift toward quieter contemplation now. Let's let the intensity of the horror fade and replace it with something more sustainable, more livable. You've been thinking about gamma-ray bursts for a while. You understand what they are, how they form, what they can do. You've confronted the threat directly, examined it from multiple angles, felt the fear and the wonder. Now you can let it settle. Not forget it, not deny it, but let it take its proper place in your awareness, part of the background, part of the context of existing in a universe that contains such phenomena. Gamma-ray bursts are real. They're dangerous. One could affect Earth someday, though probably not in your lifetime, probably not in the lifetime of anyone you know. The risk is real, but distant. Worth being aware of, but not worth constant focus. You have more immediate concerns. Your life, your relationships, your projects, your immediate contribution to the world you inhabit. The gamma-ray bursts can wait in the background, acknowledged but not dominant, present but not overwhelming. This is healthy. This is how you live with cosmic knowledge without being paralyzed by it. You know the universe is dangerous, you know you're vulnerable, and you live. Anyway, because what else can you do? Despair doesn't protect you. Fear doesn't keep you safe. Only engagement, only presence, only continuing to exist and experience and create despite the uncertainty. That's what keeps consciousness alive, both individually and collectively. So let the gamma ray bursts be what they are. Rare, powerful, dangerous events that you can't control and don't need to dwell on constantly. And let yourself be what you are, a temporary pattern of awareness, existing in the present, valuable for your experiencing rather than your duration. The beams sweep through space. You observe from here, and that's enough. Let's move into the deepest contemplation now, into the space where fear transforms into acceptance, where cosmic threats become part of the larger understanding of what it means to exist at all. We've spent time with gamma ray bursts. We've examined them from every angle, the physics, the danger, the probability, the human response. We've felt the fear, acknowledged the vulnerability, understood the threat. Now it's time to integrate this knowledge, to find peace not through denial, but through perspective, through placing gamma ray bursts in the context of everything else we know about existence, consciousness, and meaning. Start with this. You are temporary, not because of gamma ray bursts, but because of the nature of existence itself. Your body is made of atoms that will eventually disperse. Your consciousness is a pattern that will eventually dissolve. Your specific configuration of matter and energy that creates the experience of being you is unique and unrepeatable and finite. Gamma ray bursts don't create this temporariness. They're just one of many ways it could end. You could die tomorrow from a heart attack or a car accident, or any of countless causes that have nothing to do with cosmic radiation. The temporariness was always there. The gamma ray bursts just make it more vivid, more cosmic in scale. But temporariness doesn't equal meaninglessness. A flower is temporary. Is it therefore meaningless? A sunset lasts minutes. Is it less beautiful because it fades? The meaning is in the experience, in the awareness, in the present moment of existence. You are experiencing right now. You are aware right now. And that awareness doesn't require permanence to be valuable. A gamma ray burst could end your future, but your present, this moment, this awareness, it's happening regardless of what might occur tomorrow or in a million years. And each moment of awareness adds to the total sum of consciousness that has existed in the universe, a sum that cannot be decreased, only increased. You've contributed to that sum. You're contributing to it right now, and nothing, not even the most powerful radiation in the cosmos, can erase the fact that you existed, that you were aware, that for a brief time the universe knew itself through your particular perspective. Let's think about the scale of the universe again, but from a different angle this time. The observable universe is 93 billion light-years across. It contains an estimated 2 trillion galaxies, each with hundreds of billions of stars. The total number of stars is beyond human comprehension, 10^24, a trillion. Among those stars, how many have planets? How many planets have developed life? How many have developed consciousness? We don't know. We might be the only consciousness in the observable universe, or we might be one among trillions of conscious civilizations. But either way, consciousness is rare. Even if there are a billion civilizations out there, that's still only 1 per trillion stars. Consciousness occupies a tiny fraction of the cosmos. Most of the universe is empty space. Most matter is in stars or black holes, unconscious, unaware. Most of reality experiences nothing, knows nothing, means nothing, because there's no awareness to create meaning. You exist in the rare exception. You're one of the vanishingly small parts of the cosmos that can experience, that can know, that can create meaning through awareness. Gamma ray bursts are part of the unconscious majority. They're physics operating without awareness, energy propagating through space according to law but without intention or knowledge. You're different. You're the universe looking at itself, understanding itself, fearing itself, wondering about itself. And that difference, that consciousness, is precious beyond measure precisely because it's so rare. A gamma ray burst could end consciousness on Earth. If it does, most of the universe won't notice because most of the universe isn't conscious, but we would notice. We would experience the ending, would feel the fear and pain and loss. And before that ending, if it comes, we have now. We have the present. We have awareness. Use it. Experience it. Don't waste your consciousness on constant fear of endings. You'll end regardless, if not from gamma ray. Burst then from something else. The ending is guaranteed. What's not guaranteed is the quality of the experiencing you do before the ending. So experience fully, be present, pay attention to the reality you're inhabiting right now, which is not a reality of gamma ray bursts hitting Earth, but a reality of whatever is actually happening in your immediate experience. The gamma ray bursts are distant, abstract, possible futures. Your present is immediate, concrete, actual. Give your attention to what's actual. Let's talk about connection again, about the fact that you're not alone in facing cosmic vulnerability. Every human who has ever lived has faced mortality. Every civilization has faced the possibility of ending. Every species has existed under cosmic threats, whether they knew about those threats or not. Our ancestors feared predators, starvation, disease, warfare. They lived in constant awareness of danger, of the possibility that tomorrow might not come, and yet they continued. They built, created, loved, raised children, told stories. They didn't let the threats paralyze them. They acknowledged danger and lived anyway. We're doing the same thing, just with different threats. Our predators are cosmic, gamma ray bursts, asteroids, supernovae. But the fundamental situation is the same. We exist in a dangerous universe, and we choose to live fully despite the danger. You're not alone in this. Billions of other humans are facing the same cosmic vulnerability. We're all temporary. We're all subject to forces beyond our control. We're all going to die, individually, and perhaps eventually as a species, and yet we continue. We love, we create, we build, we ask questions, we experience beauty and wonder and connection. That collective continuation, that species-wide decision to engage with life despite knowing it's temporary and vulnerable, that's remarkable. That's humanity at its best. You're part of that collective decision. Every day you wake up and choose to participate in life, you're adding your voice to the chorus of humans saying yes to existence despite uncertainty. Gamma ray bursts don't change this. They're just another uncertainty, another threat, another reason we might end. But we've always had reasons we might end, and we've always continued anyway. Continue, engage, participate. Not because you're guaranteed a future, but because the present is worth experiencing regardless of whether there's a tomorrow. Let's think about what we've learned from contemplating gamma ray bursts, about the insights that come from facing cosmic threats directly. First, we're not in control, not of the universe, not of cosmic events, not even of our own survival beyond a certain point. There are forces vastly more powerful than us, operating on scales we can barely comprehend, and they don't care about our existence. This is humbling. It strips away the illusion of human centrality, the unconscious assumption that the universe revolves around us or our concerns. But humility isn't the same as insignificance. Being small doesn't mean being meaningless. A single atom is insignificant compared to a galaxy, but it's still real, still part of reality, still matters in the sense of having causal effects. You're real. Your consciousness is real. Your experiences are real. The fact that the universe doesn't revolve around you doesn't diminish the reality and value of your existence. Second, safety is temporary and partial. We're never completely safe. We can reduce some risks, can protect ourselves from some threats. but we can't eliminate danger entirely. This is hard to accept in a technological civilization where we've become used to controlling our environment, to solving problems through engineering and science. But some problems can't be solved. Some threats can't be eliminated. We can only adapt to them, prepare for them, and accept the residual risk. Gamma-ray bursts teach us this. There's no solution to the threat they pose except resilience, becoming robust enough to survive partial destruction, distributed enough that no single event can end us. And that's a valuable lesson that applies beyond gamma-ray bursts. In any system facing existential risks, resilience through distribution is the only long-term strategy that works. Third, the present is enough. You don't need guaranteed futures to justify living now. You don't need permanence to create meaning. This might be the deepest lesson. We spend so much energy worrying about the future, planning for security, trying to ensure that tomorrow will be like today. But tomorrow is never guaranteed, not by cosmic physics, not by anything. What's guaranteed is now, this moment, this awareness. And if you can find meaning and value here, in the present, then you have everything you need, regardless of what the future holds. Gamma-ray bursts force this realization by threatening the future so dramatically that you can't hide in plans and projections. They bring you back to now, to the only time that's actually real. And now is enough. It has to be enough, because it's all you ever truly have. Let's talk about legacy one final time, from the deepest possible perspective. Your legacy is not what you leave behind, it's what you've already done. It's the sum of your experiences, your actions, your participation in reality. Every moment you've been conscious has contributed to the universe's total consciousness. Every choice you've made has affected the trajectory of reality, has altered the pattern of cause and effect in ways that ripple outward. You can't control how long those ripples continue. A gamma-ray burst could cut them short. But you can control, at least partially, what ripples you create while you can. Create beauty, reduce suffering, increase understanding, love genuinely, experience deeply. These aren't preparations for some future reward or remembrance. They're valuable in themselves, in the moment of doing them, regardless of whether anyone remembers or whether the results persist. You're not building monuments to last forever. You're creating moments that matter now, that have value in their occurrence, that contribute to the total sum of good that has existed in the universe. A gamma-ray burst can prevent future moments. It can't erase past ones. What you've done, what you've experienced, what you've been, it's permanent in the only sense that matters. It happened. It was real. And that reality is immutable. Find peace in that immutability. Your past is safe from gamma-ray bursts. Your present is all that's at risk, and if you live it well, live it fully, then even if it's cut short, you've succeeded in the only task that actually matters: being conscious, being aware, being present for your moments of existence. Let's drift into silence now, into the quiet space where understanding settles into acceptance, where knowledge becomes wisdom, where fear transforms into peace. Gamma-ray bursts exist. They sweep through the universe, beams of annihilation, consequences of stellar death. They're real, they're dangerous, and one might someday affect Earth. You know this now. You faced it directly, examined it thoroughly, felt the appropriate fear and wonder. And now you can let it go. Not forget it. It's part of your knowledge now, part of your understanding of the cosmos. But release it from the center of your attention. Let it settle into the background where it belongs. The bursts are out there, you're here, and here is where life happens, where awareness occurs, where meaning is created. Be here, fully, completely, without reservation or distraction. The gamma-ray bursts don't require your constant attention. They're cosmic background, like the expansion of space or the eventual heat death of the universe. Real, Important, worth knowing about, but not worth dwelling on at the expense of experiencing the present. You have this moment, this awareness, this breath, this thought, this experience of being alive, of being conscious, of participating in the universe's self-knowledge. That's enough. That's everything. A gamma-ray burst could end it tomorrow, or you could live for decades more, or human civilization could persist for millions of years and eventually spread across the galaxy, becoming immune to single-point failures like gamma-ray bursts hitting individual worlds. You don't know which future awaits. You can't know. The universe hasn't decided yet, or if it has, the information hasn't reached you. All you can do is be here now, experience this moment, and then the next moment, and the next, stringing together moments of awareness, building a life from the only material you actually have, the present. Gamma-ray bursts are part of the context. They're part of the universe you inhabit, but they're not the content of your life. The content is whatever you're experiencing right now, thoughts, sensations, emotions, awareness itself. Focus on the content. Let the context be what it is. The universe contains gamma-ray bursts. The universe also contains you. Both are remarkable. Both are part of the cosmic story. And for now, for this moment, you're here to experience it, to participate in it, to add your consciousness to the universe's ongoing project of knowing itself. That's your role. Not to prevent gamma-ray bursts, you can't. Not to guarantee your survival, you can't do that either. Just to be aware, to experience, to exist as fully as you can for as long as you can. The invisible beams sweep through space, travelling at light speed, carrying enough energy to sterilize worlds. They've been doing this since stars first formed. They'll continue doing it until the last massive star dies, billions of years from now. And you? You're here, briefly. A temporary pattern of consciousness in a universe of unconscious forces. You're aware of the beams, can understand them, can fear them and marvel at them. That awareness is the gift, not safety. You were never promised safety, not permanence. Nothing is permanent. Just awareness, just consciousness, just the experience of being. And if a gamma-ray burst ends it, ends you, ends Earth, ends consciousness in our corner of the universe, well, it can't erase the fact that you were aware, that consciousness existed, that for a brief time the universe knew itself through you. You existed. You were conscious. You experienced reality. That's not nothing. That's everything. Rest now in that knowledge. Not in the knowledge of gamma-ray bursts, you've learned enough about those. Rest in the knowledge of your own consciousness, your own awareness, your own participation in the grand mystery of existence. The beams travel through darkness, invisible and deadly, and you observe from here, from the warmth and light of a world that has harboured consciousness for millions of years and might harbour it for it. Millions more, or might not. The universe doesn't make promises, but right now, in this moment, consciousness is here. You are here, and that's a remarkable thing, worthy of appreciation, worthy of presence, worthy of your full attention. Let the gamma-ray bursts be what they are, natural phenomena, dangerous and beautiful, part of the cosmic tapestry, and let yourself be what you are, aware, temporary, valuable, not for your duration, but for your depth. Be here, be now, be at peace with the invisible beams that sweep through space and the invisible awareness that sweeps through your mind. Both are part of reality. Both are expressions of what the universe does, and both are, in their way, miraculous. Sleep well, knowing that the universe is vast and strange and dangerous and beautiful, knowing that you're a small part of it, temporary and fragile and conscious, knowing that consciousness itself is the miracle, not its permanence, but its occurrence, not its guarantee, but its actuality. The gamma-ray bursts travel, consciousness observes, and in that observation, in that awareness, the universe achieves something extraordinary. It knows itself. You are that knowing, for now, for this moment, for however long the universe allows, and that's enough. That's everything. The beams sweep through space. You rest here in awareness, and the universe, through you, experiences both, the danger and the consciousness, the threat and the wonder, the ending and the being. Let there be peace between them. Let there be acceptance. Let there be the quiet recognition that this is how things are, how they have always been, how they must be in a universe governed by physical law. And in that recognition, find not despair but freedom. Freedom from the illusion of control. Freedom from the need for guarantees. Freedom to simply be here and now, aware and alive, for as long as being and awareness persist. The invisible beams cannot touch this moment. They cannot diminish the reality of your present awareness. They exist in possible futures while you exist in the actual now. Stay here, in the now, in the awareness, in the experience of being conscious in a universe that contains both beauty and danger, both creation and destruction, both life and the forces that end it. This is enough. This has always been enough, and it will remain enough for as long as consciousness persists to recognize it. Be at peace, be present, be aware. The gamma ray bursts sweep onward through the cosmos, and you remain here, breathing, thinking, experiencing the miracle of awareness in a universe that produces both the beams and the consciousness that contemplates them. That's the teaching. That's the truth. That's the gift. Be here for it, fully, completely, without reservation, for however long here lasts.